Good day. Today we're going to break down everything you need to know about residual current devices, or RCDs. We'll be focusing specifically on their job in providing what's called additional protection in electrical installations. Okay, so here's how we're going to tackle this. First, we'll get our heads around what additional protection actually means. Then, we'll dive into the different types of RCDs out there and, crucially, how to pick the right one for the job. From there, we'll look at the specific installation rules here in Australia, cover the all-important exceptions, and then wrap it all up with the key takeaways you can use on site. Right, first things first. What do we even mean when we say additional protection? Let's really pin down the fundamental safety role these little devices are designed to play. Now, this is the first thing you absolutely have to understand. An RCD is a supplementary safety net. It's not your first line of defense. Think of it as a crucial backup, designed to protect people when other primary safety measures might fail, or, let's be honest, when a moment of carelessness happens. The key word here is augment. It adds to the existing protection. It never, ever replaces it. And just as critical is knowing what they can't do. An RCD is not a silver bullet. For instance, it won't do a thing if someone touches two different live conductors at the same time. It also can't protect you from issues coming down the supply neutral, which is why it can never, and I mean never, be considered the one and only means of protection. So what's really fascinating is the science behind why they're so sensitive. Your standard 30 milliamp RCD, the one you see everywhere, is specifically designed to trip before an electric current can cause ventricular fibrillation. That's a lethal heart rhythm. But then you have the even more sensitive 10 milliamp RCDs. They're designed to operate so fast that they trip before the current even causes your muscles to seize up, which would stop you from being able to let go. Pretty incredible, eh? All right, so now that we've got the why down, let's get into the what. We need to look at the different types of RCDs because picking the right one is absolutely essential for it to work at all. This table lays it all out beautifully. You've got your Type AC, which is the old standard for simple, clean, alternating currents. And it's been the general go-to in Australia for years. But our appliances have gotten way more complicated, right? They've got electronics that create different kinds of currents. That's where these other types come in. Type A can handle pulsating DC currents. And then you get to Type F and Type B, which are designed for the really complex stuff you see with modern tech, like solar inverters or variable speed drive. And that all brings us to this one critical concept, the fault current waveform. You know, if there's one technical term to get your head around, it's this one. It's simply the shape of the electrical current during a fault. And why does it matter so much? Because if you use the wrong type of RCD, one that isn't designed for that specific waveform, it just won't see the fault. It'll sit there completely useless. Okay, theory's great, but let's get practical. How do we actually select and arrange these things in the real world to make sure they work when we need them to, but without causing all those frustrating, unnecessary interruptions? So there is a golden rule right here in the standards, and what it boils down to is this. The RCD has to be tough enough to handle the circuit's normal day-to-day current. You've got to figure out the maximum demand on that circuit and then pick an RCD that's rated for at least that much. And it also needs to be rated for at least as much as the circuit breaker protecting that same circuit. Nuisance tripping. It's the bane of our existence, isn't it? But the good news is you can almost always engineer it out of a system. The secret is managing leakage currents. As a rule of thumb, you want the total leakage from everything plugged in to be less than a third of the RCD's trip rating. And the best way to do that? Subdivide your circuits. Spread the load across multiple RCDs. Oh, and of course, avoid the classic mistake of running the earth wire through the RCD's sensor. That's a guaranteed way to cause problems. And this slide drives home a really key rule for any residential job. You can't just have one RCD for the whole house. I mean, can you imagine? One little fault and the entire place is plunged into darkness. So the rule is, if a home has more than one circuit, it has to have at least two RCDs, and the circuits have to be split between them to minimize any disruption. All right, let's switch gears a bit and look at the specific rules for Australia, because it's really important to know that the requirements are different depending on whether you're working in a home or a commercial building. When it comes to homes, we're talking houses, apartments, even their common areas, the rule is simple and it is absolute. Every single final subcircuit must be protected by a 30 milliamp RCD. No ifs, no buts, all of them. But the moment you step outside of a residential setting and into a commercial or industrial one, the game changes. The approach becomes much more targeted, focusing RCD protection on the areas where the risk is considered highest. So in these non-domestic places, you aren't protecting everything. Instead, the rules get really specific. You absolutely have to provide 30 milliamp RCD protection for all your socket outlets and lighting circuits that are rated up to 32 amps. And on top of that, you also have to protect any gear that's hardwired but also handheld, or any other equipment that's in a spot that might increase the risk of an electric shock. Okay, so we've covered the rules. Now for the really crucial part, knowing when those rules don't apply and what your responsibilities are when you're working on older, existing installations. This is a question that can save you a lot of headaches on site. And it's one you need to be able to answer with confidence. Because while the rules are really broad, they aren't totally absolute. There are some very specific documented exceptions. And here we go. This is the big one. The most critical exception you need to understand is where having an RCD trip could actually cause a greater danger than the shock it's designed to prevent. Think about it. What if the power to life support equipment in a hospital was suddenly cut, or to a set of traffic lights at a busy intersection? In those cases, a sudden loss of power could be catastrophic, so an RCD might not be required. So let's just quickly recap the main exemptions. You don't need to add one for simple like-for-like repairs. There's that greater danger clause we just talked about. There's also a carve-out for specific equipment known to cause nuisance trips. But, and this is a big but, the socket has to be clearly labeled to say it's not RCD protected. And finally, you don't need one if the circuit is already protected by another approved method, like an isolation transformer. Now, this is something that comes up all the time when you're working on older installations. Anytime you make a significant change, it can trigger an upgrade. If you add a new power point to an old circuit, for example, or if you replace a whole switchboard, you're now required to add RCD protection to bring those circuits up to the current standard. It's a really important way that the safety of older buildings gets improved over time. So let's pull all of those threads together. We're going to summarize the entire decision-making process for getting RCDs right, taking you from the core principles we started with all the way to compliant real-world practice. Think of this as your 5-step mental checklist for every single job. 1. What kind of building am I in? Domestic or non-domestic? 2. What kind of gear is going to be plugged into this circuit? What's the likely fault waveform? 3. Based on that, select the right RCD type, AC, A, F, or B. 4. Check the load rating and make sure the circuits are arranged properly to avoid those nuisance trips. And 5. Install everything according to the specific rules and exceptions we've just covered. And that really leaves us with a final thought to reflect on. RCDs are an incredible, life-saving technology, but they only work if they're selected and installed correctly. Making sure that every job you do provides effective, reliable additional protection, well, that's not just about ticking a box for compliance. It's a fundamental part of our professional responsibility.